Model evaluation and validation. Ensuring your machine learning model generalizes to unseen data. The foundation is three data sets. A structured approach is required to train a model efficiently and test it honestly. The first set is the training set, learning the patterns. Primary role to expose the model to the data and enable it to learn the underlying features and relationships. Action used to fit the model's parameter, weights and biases during the main learning process. Size typically the largest portion, 60 to 80% of the total available data set. Second set is validation set, hyperparameter tuning, the inner loop of optimization. The validation set is a crucial holdout sample used during the development phase to assess the model's performance on unseen data and optimize setting like learning rate, number of layers, or regularization strain. This guides configuration without touching the final test data. Its primary function is to prevent overfitting to the training data. The third set is test set, unbiased final report. Primary role to provide a final, objective and unbiased estimate of the model's true generalization ability. Rule must be kept completely separate until the model is finalized and or hyperparameter tuning is complete. Outcome: the performance on this set is officially reported measure of the model's success on a new real-world data. The train validation test set split. The reason for the three-way split is to maintain the integrity of the performance score. The validation set is used for internal tuning. The test set is reserved for the final external judgment. Using the test set for tuning even indirectly leads to an optimistic score when the model faces truly novel data. The isolation of the test set is the golden rule of evaluation. Beyond a simple split, cross-validation, a more robust technique for estimating model performance with limited data. What is k-fold cross-validation? The k-fold concept, the entire dataset or the non-test portion is partitioned into k equal sized subset called folds. The process is repeated k times using a different fold as the validation set in each iteration. Maximized data utility. The process ensures that every data point gets to be in the validation set exactly once and is used for training in the other k-1 iterations. The final performance is the average of k scores. K-fold CV visualized. Iterative validation. In each of the 5 folds shown in the diagram, one section of the data, that is fold 1, is used for testing while the remaining 4 folds 2 to 5 are used for training. This iteration across all folds produces a stable low variance performance score which is less prone to the randomness of a single split. You can see the picture to understand it better. Differences between simple split and cross validation. Simple split. High variance estimate performance is highly dependent on the specific random data points chosen for the fixed validation set, which can lead to misleading score. Cross validation. Low variance estimate. The result is the average of k runs, minimizing the impact of any single lucky or unlucky split, leading to a much more stable and reliable measure. Key difference to maximizing data utility. Simple split. A large fixed portion of the available data is reserved for the validation test sets and is never used for model training, potentially reducing the amount of information the model learns from. Use case ideal for massive datasets where reserving 20% still leaves millions of samples for training. Cross validation maximizes the data usage. Every data point is used for training in k-1 iterations, ensuring a more robust and information-rich model training, especially critical for smaller datasets. Use case essential for small or medium datasets where maximizing the training sample size is crucial for performance. Thank you guys for watching. If you have any questions, please comment down below.